Hello, welcome everyone. If you're here, feel free to say hi in the chat or just give it a minute or two for people to join and then we'll get started. But welcome if you're here. I'm just going to check that I can see the chat and your messages coming through. And then we'll start looking at this webcast today on sequences. And that'll be great. So one sec, I'll just get myself ready to share the screen. Right, so let's have a little look. I'm just checking as I can't see any messages coming through. But if you are, please do feel free to say hi in the chat if you haven't already. And as I said, we're going to look at sequences today, which is a big GCSE topic that I'm sure you've met before prior to GCSE. And hopefully that'll be something that we can kind of revise and consolidate today. So that'd be brilliant. I'm going to share my screen now. And if you can let me know that you can see this, hopefully it'll be nice and clear. So as I said, we are going to look at sequences. I'm just sharing that with you now. Cool. Right, so let's have a little look. As I said, I can't see the chat at the moment. I'm just going to try and resolve that. But either way, I'm going to get started because hopefully this would be a nice topic to go through, revise and check that we understand and know. So sequences is a big one. And since the GCSE sort of reformed a little bit a few years ago, there are a few types of sequences that were thrown in that we now need to know and understand. So we're going to have a little look at that as well. So I'm just about to start. Hopefully everyone can see that fine and we'll get cracking with this. So here we go. So that's me, I'm Max, and I'm head of maths at Snap Revise, and I've been teaching maths since I graduated, so about the last 4 or 5 years now. And yeah, been doing these web classes on YouTube, as well as a lot of stuff with Snap Revise rather on the platform. And it's been an interesting year, obviously, and we've got some obviously really good content to go through tailored to the GCSE. I'll talk a little bit about that later on. What we're going to do today is look at what is meant by a sequence, understand how we use the notation, the rules, and talk about what an arithmetic sequence is. I'm not going to go into geometric sequences or quadratic sequences, but we will look at some of the notation that we have to use and be familiar with because it does catch people off a little bit. So we'll go through that now. The GCSE content is geared up for AQA, Edexcel and OCR. This is one of the topics that runs through all the GCSE. So it doesn't matter what exam board you're doing the GCSE with. This is definitely a topic that will come up. So hopefully it's stuff you're familiar with. Do let me know if this is something you've done before, you're feeling confident with. And it'll be, yeah, as I said, great to see your messages in the chat and feel free to share answers and ask questions as we go. Right, so to start with, just a little recap of some kind of key ideas. Obviously, this one here, we might think this is really basic and straightforward. This is dealing with multiples. So multiples of 1, we don't typically think of necessarily as a particularly like interesting sequence, but they are multiples. They are going up in ones. So this would be a sequence. Here, obviously, the even numbers starting from 2, which is nice, would be a sequence, and so on. So the times tables are basically very basic sequences. And that's kind of how we relate everything in this topic to looking at a pattern and finding a rule for it. And typically, we're going to use the times tables. We're going to use what we already know. So I'm sure everyone can kind of carry these on, and we're quite happy with what multiples are. So multiples are just numbers that follow a times table, and that is obviously something we should already know and hopefully is prerequisite knowledge. So excellent. What we're going to look at today though is sequences. So for this topic, I'm going to define what a sequence actually is in terms of mathematics and also look carefully at the notation because as I said, this used to throw me off. It was a little bit confusing to start with. And then we kind of get used to this subscript thing. So a sequence is basically, within mathematics, it's a set of numbers. sort that pen out. There we go. A sequence is a set. Whoops. Sorry, guys. The pen's been a bit strange here. Set of, my goodness, numbers. Apologies for the strange handwriting. Here we go. In a particular order that follow a pattern. So in a particular order, maybe this pen will start responding soon. Particular order, basically following a pattern. So a set of numbers following a pattern, and we'll dive into this. So a sequence is, let's try it down here, a set of numbers following a pattern. Apologies a little bit about the handwriting there, guys. So 1, 2, 3, 4, 5, 6, 7, quite straightforward. The notation UN, U subscript N, represents basically what we call the nth term rule. The nth term rule of the sequence. Let me know if you've seen this before, of the sequence. So we would use UN to give the nth term rule. And if I said, for example, what is U2, what is term number 2, in this sequence, that would have the value 2. So this means the second term, and this means the nth term. So if I said U10, I would be saying, what's the 10th thing in this list? Okay, cool. So I'm going to keep going, but hopefully that's fairly straightforward. And I'm hoping that this notation is familiar, but if not, I will try and explain this as we go. So we're going to look at the actual sequence formula and how to sort out the nth term rule given the sequence we've got. So basically, we can define a sequence with a formula for either the nth term, and this is the bit that I think can be quite tricky at GCSE with the notation. So the nth term, where we use U subscript N, and for this would just be the sequence of the 1 times tables. So the nth term rule of this would just be N. If I want the 10th term, it's 10. If I want the 100th term, it's 100. And then the next term, sometimes we can define a sequence in this kind of term to term approach. The next term, we can also define it as UN plus 1 is found by taking the term we're on and adding 1 to it. So although the different types of notation here are very close together, they seem very similar, these subtleties can really throw people off. And particularly this style of defining a sequence, I know that this catches a lot of students out at GCSE, so we're really going to explore this today. I'm just going to confirm we're all good with this, and then I'm going to keep going with some obviously trickier examples of sequences than just the 1 times table, but just setting up the notation here is what we're looking to do. Right, here we go. So I'm going to move this on. So for example, the square numbers, if we were using this notation, U of N, how do I find the nth term of the square number sequence? It is just N squared. It's the number we're on and we square it. So that sequence would obviously go 1, 4, 9, 16, 25. And if I wanted the 5th term, oh, okay. So for some people, this might be something very new, this type of notation, but no problem at all. Don't worry if that's the case. This is really actually worthwhile going through. So U5, this just means term number 5. And how do you get term number 5? You take the number 5 and you square it. So U5 is 5 squared, which is 25. So that's how this notation works. It tells you that whatever term you want, you take that number and you square it. If I want the 10th term, I do 10 squared. So the cube numbers, in a very similar way, would be n cubed and that would go 1, 8, then 3 cubed is 27, 4 cubed is 64, 5 cubed is 125, and so on. So that's an example of how to use this notation for these sequences. Right, I'm going to keep going. Here we go. Now, let me know if you've seen these sequences before. So the Fibonacci numbers, this is an interesting one. And this is where I'm going to use the slightly different type of notation to define this. So for those of you that have seen Fibonacci numbers before, the Fibonacci sequence before, you might be aware that the sequence goes, yeah, excellent. So some people have seen this before. The sequence goes, some people start from 0, but 1, 1, 2, 3, 5, 8, 13, and so on. And feel free to describe the rule, because actually it's probably easier to start with to describe this rule in words. So what actually happens here? What are we doing from term to term? It's not like what we just saw. It's not sort of a times table or anything like that. How are we going from term to term in this sequence? And it does sometimes take a few terms for us to realize what's actually going on. This is quite tricky. If you haven't seen the Fibonacci sequence before, it could be quite tricky to work out what's going on with these numbers. But do let me know if you have worked out or you do know the underlying rule. And well done if you've got it. Basically, the rule to get from term to term is to add the two previous. So if I do 1 plus 1, I get 2. If I do 1 plus 2, I get 3. If I do 2 plus 3, I get 5. And so on. Brilliant. Well done for the suggestions there and the comments. You add the two previous terms. So this is where that notation comes in, where we need to be careful. So if I want u of n, superb, guys. Thanks for that. Yeah, we're adding the two previous terms. The way we can denote this, because it's often a lot easier to just say that. I've spotted it. I know what the sequence is doing. I can see the pattern. You're basically going, well, it's the term before un minus 1 plus the term before that un minus 2. So this is sort of like almost like a recursive way of explaining it. So for example, if I wanted the fifth term, that would mean it would be the fourth term plus the third term. Now I know this subscript n minus 1, n minus 2 might look a bit confusing, but n minus 1 and n minus 2 are just the two numbers that would come before n. So if I'm looking for the 10th term, this rule is basically telling me I need to know the 8th and the 9th term to be able to add them up and get the 10th term. And this is where this sequence is quite different to a lot of the sequences you've done perhaps in school where you've done nth term rule before, because it relies on you knowing all the terms before. You have to know the two previous terms. So if the sequence was just like n squared, you can just take the number and square it. Whereas for this kind of recursive sequence, you need to know the two numbers that come before the one you want. So it is a little bit more involved. But I do appreciate that this notation does confuse people. So do let me know if that makes sense or if not. But hopefully you can see that what we're basically saying is to get the next term, you add the two previous, and we're just defining it in that u subscript n way. I know that a lot of people really dislike this. Where's n minus 1 come from? What's that? It just means the term before n. So un is equal to un minus 1 plus un minus 2. So if I want the 20th term, it's the 19th plus the 18th term. So that's all that that notation means. And that's, if you can get familiar with that, it does really help, especially in like an exam situation, because a lot of people see this notation and it really panics them or puts them off, and they start minusing 1 and doing weird things. It just denotes the term before. Okay, so let me have a little look. I'm going to keep going. So triangular numbers, I'm going to write what these are. And again, you might have seen these before. So basically the way that these work is basically what you're doing is you're adding, for each term, you're adding up to n. Okay, so this rule is un minus 1 plus n. Now this is a little bit trickier, but you might have seen these before. So these numbers go 1, 3, 6, 10, 15. And the reason they're called triangular numbers is if you think about the little triangles you could form, you do 1 and then you add another 2, and then you do that and you add another 3, and then you take that result that was a little bit off. And then you add 4. And it sort of grows like a triangle. So that's how these ones work. These are triangular numbers. Let me know if you've seen this before. And again, it's all brilliant if you can be familiar with this setup for sequences. Now, we are going to look at finding some nth term rules and doing some exam paper practice shortly. But what I want to just do now, we're just kind of looking at an overview of the different types of sequences that can come up. We also have these ideas of geometric and quadratic sequences, which I did mention that I won't fully go into today, but how these behave. Geometric sequences are basically multiplying by a common ratio. There's like a kind of scale factor or power that it follows. Yeah, excellent. So some of you have seen this before. I think this is a super relevant type of sequence for a number of reasons, but sometimes when we look at like compound interest, ideas like that, this growth rate being a multiplicative factor is very different from just adding on the same amount, and things grow very quickly. So what we've got, if we think about it, like r squared, r cubed, r to the 4, and so on. This would be multiplying by r, and this would be the sequence of r to the power of n. And if we're thinking, oh, cool, and well done if you've had a little look at the triangular numbers. There are some really cool things you can do with the nth term rule there, yeah, to do with kind of quadratic sequences and so on. So very well done. Yes, now this idea of like a geometric sequence or geometric progression, this builds into A level as well, but it's this idea of like a multiplicative factor that's making it grow in a kind of exponential fashion. So for example, if the rule was 2 to the power of n, the sequence would go 2, 4, 8, 16, 32, and grow a lot quicker than if it was just adding 2 on. So this is what we mean by a geometric sequence. So if we talk about something being arithmetic, it's additive. It's adding on a common difference or common amount. If we talk about it being geometric, it's multiplicative. So it's timesing by a common ratio or a scale factor. Now, quadratic sequence is something of the form, I'm sure you've done a lot of quadratics in a number of different ways throughout the GCSE, lots of different little subtopics. But this is following something where there's an n squared involved. So for example, if we had n squared plus 2n plus 3. So a quadratic sequence may look like this. And as I said, I won't go into it in too much detail today. But yes, so very good. So the geometric progressions come up in additional maths as well. Some of the kind of further maths qualifications, you see some of this stuff in as well. But this is all really relevant to not only the GCSE, but beyond that as well. So quadratic sequences you may have seen before. And this is basically when it's increasing or decreasing, but then the amount changes, but the second difference is the same. So it goes up by 5, then 7, then 9, then 11, then 13. So the second difference is increasing by the same amount, the difference of the differences. And that would mean that it's a quadratic sequence. So we need to learn how to look out for those kind of sequences as well. Brilliant. Right, what I'll do, we're going to look at some exam questions as well now, and how this could come up, and also being really able to tackle the notation. So just if you guys could give me a quick indication of how confident you're feeling with this topic, all the stuff I said, I know I kind of whizzed through lots of different ideas quite quickly there, but if you could just give me an indication, like a 1, 2 or a 3 on how confident you're feeling. It might be something that you've done a lot of in the past, or it might be a topic that actually you think, I'm going to need to, there's some new things here that I've never heard of. I'm going to need to do some work. So feel free to give me a quick 1, 2 or 3 indication of how confident you are with that sort of stuff. That would be brilliant. And then, as I said, we'll look at some exam style questions and go through the techniques. So that will be great. Super. So I'm going to move this on. No worries. So don't worry if it's kind of like in the middle or you're a little bit unsure. This is a topic to certainly be aware of that we can practice. So here we go. This is using that notation now, like an exam style question on it. And it says a sequence is defined by the term-to-term rule, un plus 1, so the next term on from un, is equal to un squared minus 8 lots of un plus 17. So what this means is to get the next thing, you square the one you're on, you minus 8 lots of it, and you add 17. So if you guys want to quickly give this a try and see if you can follow this notation, if the first term is 4, what do we reckon that the second term would be equal to? So we're trying to find U2 and U3, term number 2 and term number 3, following this rule. So don't get too caught up on the notation, but have a little think. What do I do to the term that I've got? I know the first term is 4. I want the second term. So U2 is effectively the UN plus 1. What am I doing with U1? What am I doing with the value of 4? So this will be, and do let me know if you've got a value. So you will take U1, you square it, you minus 8 lots of it, and you add 17. So U1 was 4. So I'm going to do 4 squared minus 8 lots of 4 plus 17. It does look very confusing. When you first see this, it seems like there's way too much notation for a short 2-mark question. Absolutely. And this is the thing that will really sort of stand you apart. If we can get our head around what effectively is going on here, what is the rule? They've told me that the first term, U1 is 4, and there's this whole lot of U's and N's and subscripts, but basically, how do I get the next term? The one I'm on, I square it, I minus 8 lots of it, and I add 17, and that will come out as 1. So U2, the second term, is now 1. Okay, so the sequence basically goes 4, 1, and then something, and we're looking for that as well. So U3 will be the second term, U2, that we just found, squared, minus 8 lots of U2 plus 17. Okay, so U2 came out as 1. So I'm going to do 1 squared rather, minus 8 lots of 1 plus 17. So 1 minus 8 plus 17, and that comes out as 10. Well done. So this sequence goes 4, 1, 10, and whatever. And so excellent, well done, and thank you for sharing those answers in the chat. Superb. This isn't the easiest looking skill, I'll give you that, absolutely. And I think a lot of people that would maybe nowadays that maybe sat the GCSE a long time ago would pick up this kind of question and think, what on earth is going on there? The notation looks very complicated, but actually it's just plugging numbers in. It's just substitution. You're taking this value of 4, putting it in, squaring it, minus 8 lots of it, add 17, see what it spits out. Take that number, do the same again. Very good. Thank you guys for sharing your answers there. That's superb. So yes, whilst it looks complicated, if we can kind of get over that hurdle of the notation's a little bit strange, the idea is something we can all do. It is, the algebra is very basic. It's subbing, it's substitution. It's just subbing a value in. Brilliant. So which sequence here is a geometric progression? Circle your answer. So please let me know if you've spotted which one it is. Remember, arithmetic for an additive kind of sequence, geometric for this multiplicative kind of link between terms. So have a little look. They may all well be a sequence following some rule we can spot. Very good. Thank you guys. Put answers in the chat if you brilliant. The geometric sequence or the geometric progression in this scenario is this one here, because between terms we're doubling each time. So as I said, anything that's referred to as arithmetic is additive. Anything that's referred to as geometric is multiplicative. And there may be some students here that have done some additional like statistics or the statistics GCSE. Within that, you look at a thing called the arithmetic mean, where you add all the values up and divide by how many you've got, which is kind of the standard way of working out the mean, or the geometric mean, where you multiply them all and you root it. So it's, again, tying in with the idea of arithmetic being an addition and geometric being a multiplication. But very good, well spotted there. I'm going to keep going because that was superb. So let's go, next one. So another exam style question to have a little look at. Here are the first 3 terms in a sequence, 1, 2, and 4. Very like what we've just looked at. This sequence can be continued in different ways. Find one rule for continuing the sequence and give the next 2 terms. So we want to firstly write like the nth term rule, and then what that would produce, or a different rule entirely. So the question we just did might help us think about one way we could set this up. But let's have a little think about the 2 different possible ways that this sequence could continue. So please feel free to let me know in the chat if you've got an idea of what the next 2 terms could be even, and if you've got an idea of 2 different ways this could go. Because there's only 3 terms there and you might think, oh, it's very obvious what's happening here. But we could actually interpret this in different ways. So any ideas of what the next 2 terms might be? And it's asked us to do 2 different scenarios, 2 different ways this could kind of go, 2 different patterns that could be emerging here. So do let me know. Superb. Yeah, well done. One of the ways could be that we multiply by 2, like we just saw, and it was like a geometric sort of setup. And then in that case, the next 2 terms would be 8 and 16. So that makes sense. So that's one way it could go. What else could be happening? So if it was this rule, it would be like un plus 1 is found by timesing the term before by 2, a sequence that's just doubling. So that's one scenario. What else is a scenario that could be going on here? Yeah, that effectively is this kind of rule. Yeah, we could be very good for the other idea that could be going on. Is it could be a sequence where we've added 1, then we're adding 2, then we're adding 3, then we're adding 4. Very good. So it could be something like the term we're on plus the term we're moving on to. So that term value plus the term number. Very well done for those of you that spotted that. So what we mean by that, the next 2 terms would be 7 and then 11. So for this term here, it would be 4 plus 3. So the term number we're on, U3, plus 3 would get us the next number. Then that term, U4, plus 4 would get us the next number, and so on. So that's another really good example. So basically this sequence could be going 1, 2, 4, 8, 16, 32, and so on, 64, double it all the time. The other way it could be is the term you're on plus that number. So term number 1 plus 1. Then at 2, we add 2. Then we add 3. Then we add 4. Then we add 5. And it could be increasing like that. So it might have been harder to write in terms of this notation, but hopefully we could appreciate the 2 different types of rule there and the 2 ways that this sequence could be going. So an interesting question that could cost us some time. We've got to be really kind of mindful of the time and the technique and everything here. But hopefully for everyone understanding and knowing that there's sort of a few options of where that could go, writing it and formalizing it might have been a bit trickier. But what we're going to do now, we're going to move on to looking carefully at arithmetic sequences. So this may well be something you're a bit more familiar with. So an arithmetic sequence, as I've kind of referred to, is basically a sequence where we add or subtract a number to the previous term to get the next term. So maybe have a little look at this sequence here and see if you can work out what the rule is that's going on. And this is quite a nice idea to talk through to get the okay. So 2 to 5 to 8 and so on. So what we're doing each time is we're adding 3. And so the next few terms we should be okay. Yeah, exactly. Right. So the nth term rule of this, now this is interesting. This is maybe more like something you've done before. Does anyone know what the nth term rule here would be? And this is where I mentioned earlier, comparison to the times tables, comparisons to multiplication tables. So if it's going up in threes each time, very close. Now this is a really common one that we can easily mix numbers up and stuff. It's the 3 times tables. It's like the 3 times tables, but it's not starting on 3. So it's effectively the 3 times tables shifted back by 1. So instead of going 3, 6, 9, 12, it's going 2, 5, 8, 11. So it's basically the 3 times tables, 3n, minus 1. So what we're doing is my advice for how to approach these is pick the times table it's following. So what is it jumping up in, or what is it going down in? And that is the number in front of n. It's multiples of that number. And then how have we shifted it? How far out of place is that sequence? Good. So what we'll do, we'll carry on. We'll look at some more examples of this because people get taught this completely different ways. But it's basically like the nth term rule is effectively a number times by n plus or minus something, a shift. So this number is actually the difference between terms. This is the number it's jumping up or down in. This is like the times table it's following, even if it's sort of out of position a little bit. Okay, so we're doing another example of like a method we could use for this. Who has seen this idea before? Because this is probably the type of sequence you're most likely to have seen before GCSE. Has anyone seen this sort of come up before? You might not have used this notation. You might have just said 3n minus 1. But do let me know if you've seen this before. That would be good. Right, but as I said, I'm going to go through and walk through a method. So to find the formula for the nth term of an arithmetic sequence, basically what we do is we subtract successive terms to find the difference, which we just called A. And then we're going to use the first term and A to find the constant B. Okay, so for example here, yes, there will be a session in August. Yeah, brilliant. Oh, and that'll be the next maths one. Yeah, cool. Right, so from here to here and here to here, for example, if I do 5 minus 2, the common difference is 3. It's jumping up by 3 each time. Okay, so U1, which is 2, the first term is 2, that is 3 plus something. So that is 3 minus 1. So basically what I'm saying, this is starting to look complicated, but basically B is minus 1. The rule is 3n minus 1. Now the way I think about this personally more simply is, let's just look at the numbers we've got. It's going up in threes. So it's the 3 times tables, but instead of starting on 3, it's starting on 2. So I have to minus it back by 1. And that might be the easier way to think about that. So what I'm going to do, I'm going to put a few more examples and give you guys the opportunity to try this out and see how you feel with these ones. So this one here, 45, 55, 65, 75. Now, the first thing we probably do is go, I can totally see the pattern. I know what's happening. So that's fine. I could work out the next 2 terms. But we want a general rule. We want basically a rule that will work for any value. So if I want the 100th term, I can say, oh, when n is 100, it will be this value, and I don't have to write the whole list out. So can anyone tell me the nth term rule for this sequence here? Please do let me know if you know it. And feel free to give it a try. Don't worry if you're slightly wrong. But again, look at how it's progressing, how it's evolving, what's happening in the sequence, what times table is it following, and how do I have to shift that to get me to the actual rule here. So that'd be great. Let me know if you've got an idea of what the nth term rule is for this sequence. That'd be cool. Right. So I think a lot of us are noticing that obviously there's this underlying thing of 10 is going up in tens. So that actually means the rule is following the 10 times tables. So UN is following the 10 times tables. But instead of starting on 10 and going 10, 20, 30 and so on, it's starting all the way up at 45. So I have to shift all of those numbers by 35 to get me to the correct starting point. And if you want to check your answer is right, remember, if you let n equal something, for example, if n is 3, 10 times 3 is 30, plus 35 is 65. The third term, when n is 3, is 65, so it works. So that's a really good way of checking your rule works, is put n in as one of the values and check it spits out the proper value it should have for that term. So that was great. Well done if that was hopefully clear. Let me know if you think you've got a rule for the next one. So let's look at what's happening with this sequence. And we need to think, is this sequence going up or down? And this is where it's a little bit trickier, this one, because we've got to look carefully at how it's progressing. And it is progressing by the same amount. Oh, okay, yeah. So just going back over this rule, the reason that UN plus 10 wouldn't work, this would, let me just check if that was, yeah. So the way you could have written it, because I can see actually what this is the confusion with, you could write this as the next term is equal to the term before plus 10. That is actually okay. UN plus 10, yeah. That's fine in that context if you say U1 equals 45 and you tell them where to start. That's a really good point. I see the method you use now, and that is a valid approach to do it that way. If we're using nth term rule where we don't have to define previous terms and we want to define the whole thing from scratch, this is better. But I do understand, actually looking back at the chat, the question there, UN, the term you're on plus 10 would get you the next one, but you'd then have to define the start point separately. So you're better if you can do it in this kind of multiplication way of saying it's the 10 times tables plus 35, which is effectively what we're doing. Right, now the next one, this is going down in sixes. So effectively, it's like the minus 6 times table, which although we don't technically consider that a thing, if I say like minus 6 times a number, so minus 6, minus 12, minus 18, it will follow the negative multiples. And instead of starting all the way down on minus 6, it's starting all the way up at 4. So how do I get from minus 6 to 4? I add 10. Whoops. And again, if I want to check, so this is like the minus 6 times tables, all pushed up by 10. No, brilliant. Thanks for the comments, guys. And please do continue to ask the questions because these are really good and we're kind of really pinpointing some key ideas. So this one was a little bit tougher. This was a little bit more involved. Minus 6n plus 10. It's going down in sixes, but it's not starting on minus 6. It's starting all the way up at 4. And then minus 6 each time is what's happening. So if I wanted to check it works for the third term, minus 6 times 3 is minus 18. Minus 18 plus 10 is minus 8. So it does work. So this rule helps you spit out and generate all of these terms. And it's basically like the minus 6 times tables plus 10. So very well done. I hope that was clear. We're going to mix it up and make them slightly more complicated looking here. But I'm going to give you a minute to think about these. So very well done with those. Hopefully they're clear now, those rules. We had a positive one and a negative sequence as well. We've got both arithmetic, both to do with addition or subtraction. So a constant amount. So have a look at these, which suddenly look maybe more confusing. and see if we can work out what's going on here. They are still arithmetic sequences. So let's have a little look. Cool. Excellent. Is that okay? Let's give these a go. So have a little think. They might look a bit confusing at first, but let's work out what's going on between terms. How do I get from one to the other? And then how do I shift it? So any ideas? And I appreciate it's a little bit trickier to maybe type these in the chat. So there's a bit of a challenge for you, but if you guys can, I'd really appreciate it. I'm going to go through them anyway. I just want to give you an opportunity to actually think about these. So again, they're still arithmetic sequences. They're still going up by a constant amount or down by a constant amount. I think both of these are going up, aren't they? So that would be great. Cool. So do let me know if you've got an answer or if you think you're kind of getting there with each of these. The first one, if we look at how much it's going up or down by each time, half take away a third equals 1/6. Okay, it's going up by a sixth each time. Yeah, excellent. So the easier way to do it is a common denominator if you're taking one away from the other. So we're adding on a sixth, and what's annoying is they've simplified these fractions so it's less obvious that it's going like it's going like 2, 6, 3, 6, 4, 6, 5, 6, and so on. So yeah, absolutely. Hopefully everyone's happy with that. So this is the nth term rule here would be 1/6 n. And if we take n as, say, 1, the first term would be a sixth, but we want it to be a third, which is 2/6. So we need to add another sixth on. So if we were to check it for the, say, third term, when n is 3, 3/6 plus 1/6 is 4/6, which is 2/3. So this looks a little bit trickier, but again, you can still check it. So the difference it's increasing by is adding on a sixth. So it's like the 1/6 times tables, but it's not starting on 1/6, it's starting on 1/3. So you need to add a sixth on. This one is actually potentially easier. If we can get our head around that there's this symbol pi that's been multiplied into it all, it's not actually that bad, because what we can say is, how much is it jumping up by each time? It's going up by 2 pi. Okay. So the common difference, the amount it's going up by is 2 pi. So this is like the 2 pi times tables. 2 pi n, so u of n is 2 pi n. But instead of starting on 2 pi, it's starting on 1 pi. So we're minusing 1 pi off. You could put 1 pi, but you don't need to write 1. So that's the rule. So if you want this one here, the fourth term, 2 pi times 4, 8 pi minus 1 pi is 7 pi. So it works. So 2 pi is the times tables it's going up in, minus 1 pi off to shift it into place. Okay, so these look a lot more confusing, but it's the absolutely same process and same method that we're using here. So what I'm going to do is I'm just going to have a little checkpoint to see how you guys are feeling with that. And then we'll quickly do some exam style questions and then wrap this up. And obviously feel free to ask any questions as we go. Very well done. And well done for getting, if you got the pi symbol in there, that's very impressive. Lovely. Very good. So let me know how you're feeling with this kind of content, the arithmetic sequences. What we'll do is we'll do some exam questions now. So feel free to give a 1, 2, or a 3 to indicate how you're doing. Lovely. So here we go. Here's an exam style question for you to basically find the nth term rule of this sequence. So have a go, let me know, and then I'll quickly whiz through these. That's brilliant. Cool. So this first one is going up in 4. But it doesn't start at 4, it starts all the way down at -3, which is 7 back from the number 4. So the nth term rule here is the 4 times tables minus 7. Very well done if you got that. Superb, brilliant. Right, next one. Now these throw people because they forget sometimes that don't worry about the pattern, just count how many numbers are there. 1, 2, 3, 4, and do it as a number sequence. Don't worry that what the shape is producing or how it looks. 1, 2, 3, 4, 5, 6, 7. And you quite quickly see that there's 7, 8, 9, 10. We're adding on 3 each time, aren't we? But we see that a lot easier when there's numbers. So see if you can get me the nth term rule here. The number sequence effectively goes 4, 7, 10. So let's see if we can get the nth term rule of this pattern. So this is going up in 3s. We're adding 3 each time and it's starting on 4. So very good. The nth term rule here is the 3 times tables plus 1. So it starts off with 4 and each time we add on another 3. Okay, very good. Now using that rule, this is a very common follow-up question. So it's a really good one to finish on. So 90 counters, and can we make this sequence using all 90? So basically the question is saying, is 90 a number in this sequence? Well, if we've just worked out that the nth term rule is 3n plus 1, we want to know, can that equal 90? So we just solve it algebraically. So if I minus 1, 89 equals 3n. And if I divide 89 by 3, n equals 89 over 3, which is 29 2/3. Now, since that is not a whole number, this doesn't work. But some of you may have seen this type of question before. So that tells us it isn't in the sequence. Because if it was, it would come out as an integer, a whole number. So this basically tells us that 90 counters is between the 29th and 30th term. So the 29th term would have nearly this many counters, but the 30th term would have more. It would have like 91 counters. So it kind of gives you an indication of where in the list it is, but because it's not a whole number, it's not a proper position in the list. Very good. So it's a very common follow-up type question. So well done today. Thank you guys for bearing with me there with the delays with the chat and also with the pen at the start. But I think this was a really important topic to really focus on that notation. And it looks like you guys are quite confident with the underlying ideas of sequences. So really well done. We've looked at what a sequence actually is. We've identified typical sequences and their rules. And we've really got into the detail of how this nth term rule stuff works. So very well done. If you have any questions, let me know. There are lots of upcoming web classes. I know we're kind of getting to that point now in the year where finally we're having a bit of a break from a strange year, hopefully enjoying the summer. There are some web classes regularly now happening on the weekends, just like today, that you might want to set reminders for just to keep things ticking over through the summer. So very well done and thank you so much for joining today. And it'd be great to see you at some of these upcoming web classes on YouTube. So if you can set reminders, it'd be great to speak to you at some of the web classes coming up in future and hopefully get you feeling nice and prepared and confident before schools return in September. So very well done. Yes, absolutely. So all the GCSE content is obviously relevant to the GCSEs and the IGCSEs. And then obviously further as well, the A-level stuff we do builds further into those specifications. But yes, for the most part, the IGCSE and the GCSE content largely overlap. So absolutely. Thank you guys for working so well there today. That has brought us to the end, but very well done. And thank you again for the comments, the answers and the questions. They were all brilliant and great to see. So well done, and thank you for all your hard work. Good luck with any, well, obviously the upcoming school year, but also make sure you have a nice break. Well done with what has, I'm sure, been a challenging academic year this year, being so different, but really well done. Great, thanks guys. I think I'm going to end there, but well done with sequences today, and great work. That's brilliant. Cool. Hopefully see you at a session soon. That's excellent.